Hey, it's great to see everybody joining us. I'm really excited about this presentation and this whole program. It's just a real thrill to be able to offer something a little bit unique and outside of our usual programming, our usual exhibition opportunities. And we had an amazing response to this opportunity. More than 250 SAQA members registered for today's event, and I'm hoping that a lot of them will be able to join us live. But if not, we are recording it so that anybody who isn't able to join us right now can watch it when they're available. And if you want to go back and rewatch it, of course, you'll be able to do that as well. I want to tell you a little bit about how this came to happen. About almost a year ago, I was approached by Anna Marlis Burgard, who is the editor of a special series of books based on the science being done at Johns Hopkins University. And she had been working with the Pixel Ladies, Chris Sasaki and Deb Gashat, to use their artwork for one of the books in the series. And they suggested that perhaps we could work collaboratively with some of the upcoming series. And so we've been in talks back and forth, trying to figure out how best to collaborate with the Johns Hopkins University Press. And we're really excited that this is going to be our first collaborative event. That Fierce Planets is going to be the artwork exhibition that will accompany or be connected with this wavelength book about Dr. Sabine Stanley's research. And that Dr. Stanley is herself here to tell you more about her research. And so what we're going to do is I'm going to do the usual introduction, explaining who she is and why you would want to listen to her. She's going to tell you about her research. There will be an opportunity for you to ask questions directly. If we can't get to everybody's question, Dr. Stanley has generously agreed that she will answer questions by email after the event. And if you feel inspired by anything that you hear today or by your own researches, we hope that you will create art to enter into Fierce Planets. And you'll have almost an entire year to create that art, because the call for entry will be next July. And then we're hoping to travel this exhibition of artwork inspired by Dr. Stanley's research for several years and share it with people around the country and across the globe. So I would like to tell you a little bit about Dr. Sabine Stanley. She is a Bloomberg Distinguished Professor at the Johns Hopkins University. She's in the Department of Earth and Planetary Sciences and the Space Exploration Sector of the Applied Physics Lab. She directs the Magnetism and Planetary Interiors Research Group, which is centered on understanding planetary interior processes and evolution. So what I get really excited about is that she's also working on the Mars InSight mission, looking at Mars quakes. So we have earthquakes, Mars has Mars quakes. She's also using the Iridium constellation of communication satellites to track changes in the Earth's magnetic field. And she's investigating Saturn and Jupiter and helium rain and the dynamos in Uranus and Neptune. So she is looking at our own planet and then using that understanding to look at planets throughout the solar system. And as you're listening, very few of us have the background to really know all of the details of what Dr. Stanley is going to be talking about, but I would like to encourage you to ask questions to help you understand things. The last time I studied any of this was probably 45 years ago, and the science has really changed during those 45 years. And so I want to encourage you that there are no stupid questions. This is about helping you to understand what's happening in this exciting field of science, in the hopes that this will help you to be inspired in your art. And I see this as a really exciting collaboration because scientists and artists really share a great deal in common in terms of their curiosity about how things work and about how important imagination is, both to creating artwork and to doing research in science. So Sabine, I'd like to turn it over to you, and she's going to be telling us about her research. As you have questions, please go ahead and type them into the chat box. And then after her presentation, you'll also have the ability to raise your hand using that little smiley face icon at the bottom of your screen to raise your hand and then ask your question in person. But if you prefer to type, go right ahead and type. And both I and Dr. Stanley will be monitoring your questions. So thank you so much for being here. It's such an honor to have you.
Thank you so much for that introduction. I want to start, first of all, by thanking all of you for coming to this presentation. I'm so excited about this initiative. I think it's absolutely amazing to have you all here. And I want to just reiterate what Martha said, feel free to contact me with questions, anything that we aren't able to get to here. And at the moment, I have to make sure I can see the chat. So give me 2 seconds here. There's the chat. Okay. And I'm hoping everyone can see my screen. And someone will tell me if you can't. Okay. So I'm a planetary scientist, which means I'm interested in all things about planets. But what I'm going to focus on today, and what's really kind of at the core of my work, is talking about the insides of planets. And what I'm going to try to convey to you really is that it's hard. It's hard to study the insides of planets. You can't see them the way you can see, say, the surface of a planet. And I'm going to tell you a little bit about what we've learned about the insides of planets and also how we do that kind of work. So I want to start by saying just places like NASA, their equivalents like the European Space Agency, JAXA, the Japanese Space Agency, all these agencies have been sending out missions, spacecraft to planets to try and learn about them. And these missions have really provided us with stunning data about planetary bodies. And I put some examples here. Titan is a moon of Saturn. And it's the only other body in the solar system that has liquids on the surface. Earth is the other one. And the liquids, Titan has lakes and seas, but they're not made of water. They're made of ethane and methane and things like this. So these are the kinds of things we've discovered. We have found active volcanoes on Io. That little thing in the bottom left is a volcano. We found water geysers spewing out of a moon of Saturn called Enceladus. I don't know if anyone's been watching the news the last couple of days, but the new JWST telescope, in addition to staring out into the cosmos to the farthest distances it also can look at planets in our solar system. And this is an image it just returned a couple days ago from Jupiter. And the amazing thing about this image is that you can see in both the poles, the North and the South Pole, you can see that green and that orange coloring, and those are really aurorae on those planets, and you can see the hazes in the atmosphere. So this is the kind of data we can get. But notice, all of this data here is about either the surface or the atmosphere of these bodies, right? Most of the information we know about for planets is about their surfaces or their atmospheres. The deeper you go inside a planet, the less we know, okay? And that's problematic. The reason it's problematic is because it turns out that what happens inside planets ends up determining a lot of stuff that we see on the surface and the atmosphere. So we really want to understand what goes on inside planets because it'll help us understand why a planet has volcanoes, why a planet has the atmosphere it does, what makes a planet conducive to having life on it, right? All these questions require us to understand what's going on inside. So the deeper inside the planet, the less we know. That's for two reasons. One thing is planets are opaque. We can't just look inside them. So we need something to happen inside the planet that ends up producing something we can see outside the planet. Okay, so that's the game, is figure out what sorts of things happen inside the planet that have some sort of clues left on the surface. Okay, and I'll tell you some of those clues that we use. The other problem is that throughout our lives on Earth, we don't have a lot of experiences with the types of conditions that the insides of planets experience. Okay, so what am I talking about? When you go inside the Earth, by the time you get to close to the center of the Earth, the temperature is several thousand degrees. The pressure is hundreds of millions of atmospheres. And if you take a material, let's say water, and you suddenly put it to these temperature and pressure conditions, it doesn't behave the way that water does on the surface of the Earth. And so we really need to understand what happens to materials when they're in this completely different environment of these really high pressures and these really high temperatures. And it's really hard to study that. So this is why understanding what goes on inside planets is harder, but we are making progress. So we're going to talk about how we learn about planetary interiors, and I like to think of this as involving three different types of studies. The first thing we do is we try and get data. So we take spacecraft or we use telescopes. For our own Earth, we use data from satellites in orbit around the Earth, or even just here on the surface of the planet. And the data that tells us a lot about the inside of the planets typically comes from the equivalent of earthquakes on other planets and earthquakes on Earth. So that's seismology. Okay, so we get a lot of information about the inside of planets from seismology. It turns out that gravity, right? We're used to thinking of gravity as, oh, that's like 9.8 meters per second squared on the surface of the Earth. But it varies a little bit. And it varies wherever you walk on the Earth because of how much mass is under you. So we can actually learn a lot about the inside of the planet by tiny variations in gravity. How a planet rotates, so the fact that we have a day is because the Earth is spinning. How a planet rotates and how its shape deforms due to that rotation ends up telling us about the inside. We also learn about interiors from samples. So here on Earth, there are ways to get samples from deeper inside the planet, although not as many samples as we would like, to be honest. And we have some samples from other planets too, and that tells us a lot about the composition, what the planets are made of. And finally, my own sort of personal favorite, magnetic fields. And we'll talk a little bit about how we can use magnetic fields to study planets. The other thing we do is we try to do experiments. Okay, as a scientist, what you really want to do is you want to try to mimic the conditions of the region you're trying to study and see what happens to materials. So what happens to materials at high pressure and temperature? So we have developed, as scientists, some really interesting novel techniques to try and study that, and I'll talk a little bit about those. And finally, a lot of the physics of these processes and the chemistry of these processes, we use computer simulations of those equations to really try and understand what's going on and why it's happening. Can we explain the features that we kind of see? So it's really this combination of three methods to study that helps us really figure out what goes on inside planets. So let's talk about observational data. Seismology. Seismology for the Earth has really been the main driver of determining the structure of Earth's interior, okay? So the basic idea here is you have some sort of earthquake. That earthquake shakes the region, it sends waves throughout the Earth. And it turns out that the speed of those waves is determined by properties of the material it passes through. So those waves end up coming back to the surface at different points. They get detected by seismometers, and how fast those waves come in all over the surface of the Earth really allows us to completely map what goes on inside the Earth. And we can see things on the top right here is a cutout. You can see the US is on the top, that's the surface of the Earth there. And the slice on the bottom is cut out deep into the planet. And the colors here represent different seismic wave speeds. So the greenish bluish colors are wave speeds that are faster, and the reddish colors are wave speeds that are slower. And it turns out that wave speeds are faster in colder material. So I don't know if you can see this bit that says subducted slab and that green thing coming down. That is actually the Farallon plate on Earth. So that used to be a part of Earth's surface, and Earth has plate tectonics, and sometimes the Earth's surface descends back into the Earth, and that is a piece of the Earth that has now of the Earth's surface that has now subducted back into the Earth, and we can see it with seismology. So this is how we get information about the inside of Earth. Now, Earth isn't the only place that we've been able to use seismology. There are two other bodies as of right now that we've been able to do seismology on. One is the moon. The Apollo 11 astronauts brought seismometers to the moon, and they are still there today. Here's a nice picture of an astronaut doing that. And from those seismometers, we've actually been able to detect moonquakes, so earthquakes on the moon. They're a little bit different than earthquakes on Earth. They end up being a lot because the moon flexes a lot because of gravity tidal interactions with the Earth. But from those moonquakes, we can use the same sort of information to learn about the inside of the moon. And so, for example, from lunar seismology, we've learned that the moon has an iron core at the center, but it's really small. And we've learned properties about the rocky mantle layer above it, and so forth. Now, very excitingly, there are future plans to go back to the moon with new seismometers and put them in different locations, and we hope to learn a lot more about the interior of the moon from that. The other place where we've done this is on Mars, and this is the Mars InSight mission that Martha mentioned. This was the first mission to Mars that's really been dedicated to understanding the inside of Mars, right? There are a lot of, you may have heard of the rovers on Mars. There have been lots of spacecraft missions that have gone to Mars to study the surface and the atmosphere, but this one is about the inside. And the way it did this was to carry a suite of instruments that were really meant to kind of probe what is going on inside the planet. And one of those instruments was a seismometer. And in this picture, it's that little white globy thing you see on the bottom there. And this is a seismometer on Mars, and from it, we have detected hundreds of Mars quakes, okay? I'm gonna show you, this is a picture from Mars. This is you are taking the viewpoint here of the lander. It has a camera. And this is a picture of the seismometer on the surface of Mars. You can see it's a fisheye lens, so that's not real curvature on the planet, but you can see the movie of this as days go on. So that thing sits on the surface of Mars, and every time it detects Mars quakes, we learn about the inside of the planet from that. So that's seismology. Now, there are certain places in the solar system that we can kind of do a sort of seismology that you wouldn't think about. One of them is at Saturn. So Saturn's this gas giant planet. It doesn't have a surface. You can't walk around on the surface of Saturn. But Saturn's got these wonderful rings around it. And it turns out that when something happens inside the planet itself, so if there are waves inside the planet, then those waves cause perturbations that end up creating waves in Saturn's rings. And so we can watch the rings of Saturn and how they move, and from that, figure out what's going on inside the planet itself. So this is called ring seismology, and it's one of my favorite topics. All right, moving on, gravity and rotation. So this is really interesting to me. It's something that I don't think I ever appreciated well until very recently. So gravity can vary a little bit as you walk around on the surface of a bumpy planet, for example, because there might be more mass under you at one point than another, right? And so you can learn about the inside of the planet. But another thing that gravity can do is gravity can tell you about the speed of things. So if you have something that's moving really fast, the way it causes the planet to interact gravitationally and to create a shape of the planet will tell you something about the speeds of that. And people on the Juno mission, which is a mission at Jupiter right now, have used this technique to actually map the winds that you see on the surface of Jupiter. So if you've ever gotten a chance to see Jupiter, it has these beautiful banded winds on it. And those, some of those bands, so a band might go to the left, another band will go to the right. So they kind of have this zonal feature, kind of like the jets we have in our atmosphere, which you've experienced if you've flown in an airplane. But we've never known how deep those winds go. Are they just kind of at the surface? Does the whole planet do that zooming? And with gravity and rotation, we've actually now been able to figure out the depths of these winds, and they go down several thousand kilometers inside the planet, several thousand miles, you could also say. So that's really been an interesting technique for discovering what goes on inside planets. Gravity has also told us about this amazing structure of the inside of Jupiter. So Jupiter is this gas giant planet. It's mostly made of hydrogen and helium, okay? But again, you take hydrogen and you squeeze it under incredible pressure, and it doesn't behave the way hydrogen gas does in our regular experiences. And we've learned about all these different phases of hydrogen, something called metallic hydrogen, which is not something, you don't think of hydrogen as a metal, but inside planets, materials can do really interesting things. We also have samples from planets. This is one of my former grad students who got to go to a NASA center and hold one of the samples from the lunar mission. So the Apollo missions to the moon brought back 370 kilograms of rocks from the moon. And we use those now to really try to understand what the moon is made of, what the composition is, what the conditions were like when those rocks formed. So this is one way we also learn about other bodies. Now, the moon's the only place where we've currently gone to, grabbed a rock and brought it back. But we're also very fortunate that the solar system provides us with rocks by itself through meteorites, right? So every time you see a shooting star going by, that is something from far away coming and impacting the Earth. And some of those things actually make it to the ground and we can find them. So meteorites are a really great way to learn about different bodies in the solar system. We have meteorites from Mars. This one in the bottom left here is a meteorite that came from Mars. We have meteorites from the beginning of the solar system. In the bottom right here, this carbonaceous chondrite, that is the oldest known object in the solar system. And it dates to 4.567 billion years ago. And that's what we base our age of the solar system on, is the oldest thing we've ever found in the solar system. An amazing thing about meteorites as well is sometimes they come from, maybe you have an asteroid that got broken up because it crashed into another asteroid. And when it breaks up, we actually get a view of the inside of the planet or the asteroid, right? And that's not something we can't break up the Earth. We don't want to break up the Earth and go look on inside, right? But we actually have asteroids that have broken up and parts of their interiors, the deep interiors of them, have come to Earth. And that's what you see in the top here. So this iron meteorite on the left, that is from a metal core of an asteroid. So a lot of the times when we're trying to understand what goes on in the very deep interior of our planet, so Earth has a metal core as well, we look at meteorites that are metal cores from other bodies to try and understand what might be happening in ours. And then you have my favorite meteorites, which are these things on the top right here called palasites. And they're actually a mixture of that boundary right between the core of a planet and the rocky mantle of the planet. So the green stuff you see in here, these nice gem-like things, that's a mineral called olivine, which is a rock that forms at high pressures. And the matrix around it, the grayish stuff, is metal, is iron. So this is actually a combination of those two things. And now I'm noticing that there's a lot of questions in the chat that I completely missed, but we will definitely go that. So there is a question, does Mars have tectonic plates and faults like the Earth? That's a great question. Mars doesn't have plate tectonics, but it does have what we would call tectonics in the sense that parts of the surface are still deforming and crushing. So Mars has what we call rifts. Mars has what's called extension. So some of the crust is opening up, squishing together. So a lot of the Mars quakes we see come from that. And oh yeah, great question. How can you tell where the pieces or meteorites have come from? Thank you so much for asking that question. So here's an amazing thing about rocks. Rocks are usually a conglomerate of a bunch of minerals, right? So you can see that really nicely in the bottom right one here. And inside the rock, these minerals can also hold little packets of the atmosphere of the place where they formed. And a lot of the rocks and the little gas packets have distinct, what are called isotopic signatures. So Earth's atmosphere has a very specific isotopic signature. For example, how much oxygen. So isotopes are when you have an element that has different numbers of neutrons in it. So you could have oxygen 16, oxygen 17, and 18, and they all have the same number of what are called protons. So they're all the same element, but they weigh different. They have different numbers of neutrons. And so Earth has a very specific oxygen 18 to 16 ratio. Mars has a completely different one. The moon has a completely different one. And so we end up telling where most of these bodies come from based on what are called isotopic signatures in them. And we've learned those because we've gone to the planets and sampled them, right? So that's really kind of how we do that. And I do agree, palasites do look like textile art, and they're very cool. All right, continuing on. We also have samples from Earth. So yes, you can walk around the surface of the Earth and grab a rock, and that's a sample of Earth, but that probably will only tell you a lot about the surface of Earth. Let's say we want to get samples from deep inside the Earth. One way we do that, it's really hard to do this, by the way, and we can't do it ourselves. It's very hard to dig inside the earth. The deepest we've ever drilled into the earth is about 8 miles or so, okay? And the earth is almost, I'm going to get it wrong in miles, but something like 3,500 miles in depth, right? But sometimes the deep parts of earth come to us. One way they do that is when we have magmas come up, for example, in volcanoes and stuff like that. Sometimes they carry these things called kimberlites, and kimberlites have diamonds in them. Now, diamonds are a form of carbon under high pressure, right? So the way we form diamonds is we take graphite, let's say the stuff in your pencil lead, and we put it under really high pressure, and the carbon atoms change their structure and they become diamond. Now, when diamonds form deep inside the earth, they sometimes have these things inside them. They don't fully form just pure diamond. They have other stuff inside them. And you can see a picture of one in here. This is what's called an inclusion, and this is a garnet inclusion. So garnet's another mineral. And so a little bit of garnet got stuck in the diamond. Now, if you're a jeweler, you hate this, right? Jewelers want pure diamonds. If you're a geologist, you love this, because what this is the diamond formed around the garnet deep inside the earth and then brought it up, almost like in a time capsule or a completely packaged capsule. So we can actually learn about the inside of the earth by going into this and looking at this garnet and figuring out all sorts of information about it. So that's another way we get samples from the earth. All right, now magnetic fields. This one's my favorite, okay? So many planets in our solar system and also a couple of moons in our solar system have magnetic fields that are generated inside of them. And this is just a nice image. We can't see magnetic fields, but we can feel them if you have magnets, for example, right? But if you could see Earth's magnetic field, this is kind of what it would look like. It has these long arc spaghetti-like field lines that go from one hemisphere near the, let's say the South Pole here, and zip around to the other hemisphere, the North Pole here, okay? So these are what magnetic field lines look like on Earth. Now, those magnetic fields are really important for providing information on two really hard to reach places, okay? One of them is the deep interior, and that's because those magnetic fields, they get created in the core of the Earth. So the Earth, about half the radius of the Earth is rocky mantle, and the other half is an iron core. And it's in this iron core that magnetic fields are generated. And this is from a computer simulation of one of mine, of those magnetic fields being generated in the core. So those magnetic fields get created deep inside, but then they make it out of the planet. They don't care about the rock in between, they just come out. And so we can observe them at the surface and what they're doing and actually figure out what's going on deep inside the planet. So that's one reason that magnetic fields are really important. Another region they can tell us about, I don't know if you call it a region, I'm cheating a little bit here, is the deep past, okay? So when rocks form on a planet, they usually start in a molten state and they cool down to solidify. And when they do that, if you have the right type of rock, it can actually freeze in the magnetic field at the time the rock formed. So if we can find old rocks, which we can, so you find a rock from 1 billion years ago, if it can keep a magnetic field, if it's a magnetic carrying rock, you can actually figure out what the Earth's magnetic field was like 1 billion years ago. And so we've actually used this. Magnetic fields were really the most important part of the story when we learned that plate tectonics was a real thing for Earth, and that happened in like the 1960s. So magnetic fields are really important to tell us about our past and also about our deep interior. Now, when we try to visualize magnetic fields, right, I told you there are these stringy lines, and you could imagine if we tried to do this and tried to understand what we're seeing here, that's really hard. So what we usually do is we take these magnetic fields and we find a way to represent them on the surface of the body. So here, the colors represent the sign or the polarity of the magnetic field. So if the magnetic fields are coming out, you might see red, and if magnetic fields are going in, you see blue. And the intensity of the color tells you how strong the magnetic field is, right? So here, the strongest fields on Earth are coming out of the polar regions, okay? And then we get really frustrated because we want to see the backside of the planet, and you can't do it in this type of view. So what we do is we kind of slice through the Earth and pull it open, and we get a map like this. So in a picture like this, the right-hand edge here is exactly the same location as the left-hand edge. So we've kind of morphed out a sphere into this feature, just like they do with maps. So this is what Earth's magnetic field looks like. You can see it's got this strong feature in the southern hemisphere and strong feature in the northern hemisphere, and then it's weaker as you get closer to the equator. But the Earth's magnetic field also changes in time, and we have records of this. One of the ways we have records is from those rocks in the surface. But it turns out that since about the 1600s, we also have navigation records, because many of the ships, particularly that were crossing the Atlantic, would do navigation with compasses. And so there are all these logs of ship records. And in my head, I've never seen them, but in my head, it's someone's wrote, it's this day of this month, ... and the compass is pointing in this direction. So people have used those records and gone back in time and recreated what Earth's magnetic field was like in the past. And you can see here, stuff is moving around. The Earth's magnetic field is not fixed. It moves around, and we can track these things and see how they move. The Earth's magnetic field on longer timescales also flips. So right now you see that it's mostly blue in one hemisphere and mostly reddish orange in the other hemisphere. We know that about every 500,000 years or so, that changes. So red ends up in the northern hemisphere, blue ends up in the southern hemisphere, and that's called the magnetic polarity reversal. So we know that from rocks that have retained magnetic fields from the past. So we're really trying to understand why this field is changing the way it is, because it really tells us about what goes on deep inside the Earth. Now, other planets have magnetic fields. They don't all look like Earth's. So these are the planets in the solar system that have active magnetic fields being generated today. And you can see that Earth, yeah, it's got the red in the south, blue in the north. Mercury's kind of the same, red in the south, blue in the north. But it seems that even just visually, you can tell there's differences here, right? Then you go to Uranus and Neptune, and they look completely different. They're a mess, right? And so I actually spent most of my PhD trying to understand why Uranus's and Neptune's magnetic fields look so different than the other planets. And there's a question in the chat that asks, why would the polarity reverse? That is an excellent question. We wish we knew. This is an active area of research. We don't fully understand why a magnetic field flips, and we also can't predict them. The last time it happened on Earth was 750,000 years ago. On average, they happen about every 500,000 years, so technically we're overdue for a reversal. Now, if you go to other planets, we don't really know if they reverse because we don't have as much data from them to tell. But it turns out the sun also has a magnetic field, and the sun's magnetic field flips every 11 years, like clockwork. So, and we don't know either why. So what we tell people when they kind of ask us about this is, if you're a scientist, you say something like, well, it's a chaotic process and the field is happy to be of either sign, and there's so much perturbations going on that every once in a while it just flips. But that doesn't really explain the mechanism and doesn't help us predict. So this is a very active area of research. Another great question in the chat: how does the magnetic polarity reversal affect animals that use the magnetic fields for location? That's a great question. Short answer, we don't know. Longer answer, we know they've survived, right? They've made it through other polarity reversals. There is no correlation between reversals and loss of animal life. So we know they've made it. I think a lot of recent studies, there was a study, I can't remember who it was by, they were looking at birds, and some birds use magnetic fields to help in navigation, but it turns out they don't only use the magnetic field. So the theory there was, yeah, okay, if you suddenly had a polarity reversal, it's not like all the birds would suddenly kind of fly north when they're supposed to go south or anything. They do use other things to help navigate as well. So I guess other things would compensate in that scenario, but we don't really know. All right, so how are these magnetic fields generated? So the 101 course here, it's really important that you have a few things, okay? To create a magnetic field, you have to have something in motion. Fluid, so you have to have something that's a fluid, a liquid, and it's got to be moving. And it's got to be moving in a really complicated way. And in this picture, I'm trying to show that with these little spirally yellow things. Turns out that helical spiral motions are really great for creating magnetic fields. The other thing is, in order to create magnetic fields, you have to be in a material that's a really good electrical conductor. You have to be in a metal, for example. So when we have a planet that has a magnetic field, you can already learn a lot about its insides. You've suddenly learned, oh, it has an electrically conducting material inside of it, and that material is moving. And that's something that there's really no other way to learn that without having something like a magnetic field. So those are the kinds of things that we can really learn about the inside of a planet when we study them. So now there's a question: what's the range in the period to flip the magnetic field? Is there any other correlation with any other happenings on Earth? So that's a great question. It is really kind of a random or a chaotic process in the sense that if you add up the number of reversals we know about in the past and divide by the total amount of time, you get 500,000 years. But there have been tens of millions of years where there's been no reversal. And then there's been times when it's kind of reversed quite a lot. So there's not really a good understanding about what causes those things, to be honest. And there's no real correlation. There's not so you'll find papers out there in the scientific literature. Some people think it might have to do with differences in how much heat can come out of the earth at different parts in time. So Earth's core is covered by the mantle. The mantle is also doing its own thing. The mantle convects, rock moves around in the mantle. So it might be related to how much heat you can pull out of the earth and out of the core at that time, but it really is not well known. And we don't know how quick a reversal happens. There is some evidence that they can happen in about 100 to 1,000 years, but we don't really know. All right, so one way we study magnetic fields and their reversals and their everyday moving arounds is with computer simulations. So we kind of understand the equations that govern fluids and magnetic fields. And although we can't solve them on pen and paper, we can tell a computer to solve them. And so when it does, first of all, this is really hard to do. We use the biggest supercomputers in the world to do this. And when we do, we get images like this. So this is kind of a snapshot of data about the magnetic field. So these yellow things here are probably magnetic fields in this image. And you can see the blue and red things. Those are the fluid velocities. And so you really get a picture of what's going on inside the dynamo to create this. And you can see our simulations. This is a simulation as well, and it can produce reversals. So here at the top, this is a kind of different times. At the top, you can see the spaghetti lines coming out of the north are orange. And then here you see now they're starting to be blue. So the field reversed in that time. And here's what the field looked like. Kind of that third picture down is the field during a reversal. And then you come back around and eventually it flips again. So these are the kinds of things we can create in our simulations to help try and understand what we're seeing going on inside the planet. I also want to mention that it's really important when we're doing science like this to work with artists. There's so much in terms of visualization and understanding that can be done when you represent things visually. I had the great privilege of working with an artist through this program at Hopkins called the Hemi Mica Extreme Arts Program, where interns at the Maryland Institute and College of Art were paired with scientists and in the Extreme Materials Institute, which I'm a part of here at Hopkins. And they worked with us for a summer to do some sort of art project. And we had this wonderful artist, Yi Zhang, who created this animated video that also has, if you go to the YouTube channel where it is, also has a narration on top of it. And it really tried to explain a lot of things going on with the magnetic field. So this was a really great partnership that we did to try and help understand planets. She also helped us in a couple of other things. We created a couple of GIFs to help understand certain features. On the left here, this was one done for Saturn to understand where helium rain is happening. This is meant to be helium rain. This is the formation of something called the lunar magma ocean on the moon. Okay. She also created the logo that I use for my group. So it's been absolutely wonderful working with her. All right. So those were data stuff. Now I want to talk a little bit about experiments that we could do to try and understand what happens inside planets. Now, here's the key thing. You can take a material that we're very familiar with on the surface of the Earth, water, and you stick it under pressures and temperatures inside planets, and it's a completely different beast. So what we're really trying to do, and that's what in this artist rendition of this is meant to be Neptune, and the artist rendition here, it's meant to show that you take something like water and it can go from being a gaseous form in the atmosphere to more sort of the standard liquid oceany type thing here to a completely different phase as you go deeper and deeper inside the planet. So scientists are trying to figure out what these are, and there's not an easy way to do this. You can't just kind of plug in numbers in an equation and say, oh, at this depth and pressure, water must do this. You really have to kind of go to the fundamental equations for chemistry. A lot of this is done with, if people have heard of Schrodinger's equation, quantum mechanics. So those sorts of things really tell you what happens to these materials. So how do you do these experiments? Well, you want to create a really high pressure environment. And that means you have to squeeze something a lot, okay? The way this is done these days, there are a variety of different ways. One way is with diamonds. So it turns out that diamonds can also be used as tools. If you take a sample, this is called a diamond anvil cell. If you take a sample of some material and you want to squeeze it under high pressures, you stick it between the points of two diamonds, and then you squeeze the outer part of the diamond, and that creates a really high pressure in the center. So this is something that's done in experiments. Another thing you can do is you can use shock waves to slam into a material really hard. And when you do that, you cause it to a shock wave to compress the material for a very short amount of time. And that's what is done at these giant accelerator facilities, such as, so there's a place called Sandia National Labs. There are other ones as well, where they're basically giant lasers that can heat up a sample and create the types of shocks you need to compress a material. And so this is the Sandia National Lab experiment. And this picture always blows my mind. So this is an entire room. I don't know if you can see the people up there. And then if you want to look at a sample, so these are X-rays being shot through a sample, tiny little sample in the middle. And then you look at what the pattern of those X-rays gives you to try and learn about what's going on inside the bodies. Other experiments we can do, so we use computer simulations to try and figure out magnetic fields. We can also try to create our own magnetic fields. So these are called dynamo experiments. Turns out this is really hard to do because you need to have a really big region to create a dynamo. And planets are great for that. Planets are huge, right? But if you want to have your tabletop dynamo, it's just not going to happen. So this is an experiment that's going on in Maryland. It's called the Maryland Dynamo Experiment. This thing is 3 meters across. It's a giant sphere, and they fill it with liquid sodium. And I don't know if anyone's ever worked with liquid sodium, but it is not a fun material to work with. It's something that will catch fire quite easily. And so there's all sorts of precautions you have to go into if you're going to build a dynamo experiment. But this is one that's running. It hasn't yet created a dynamo. And they are really kind of trying to figure out what's going on there. The other types of experiments we can do is to really understand what fluids are doing in the conditions inside planetary cores. And it turns out that, so there's a question, so yes, great question. What is a dynamo? So a dynamo really is the process where you take fluids and you move them around in such a way that you create electric currents, and those electric currents can create magnetic fields. Okay, so that is how a dynamo works inside the Earth, for example, is the Earth's molten iron moves around. It's a great conductor, electricity is generated, and those changing electric fields can create magnetic fields. Now, an amazing thing about the insides of planets is just like the surface of the planet, they're rotating. And when you have rotation, weird things happen to fluid motions, okay? So this is a video by a friend of mine. So what they've done is they've taken this pot and they've put it on top of a record player. So we use these record players a lot in our studies to understand what's called rotating convection. And then it's filled with water, and he's just pouring a creamer in the top. And if you have your cup of coffee and you pour a creamer in, you would not expect this kind of behavior to happen, right? You would expect the creamer to just kind of diffuse out and you get a nice creamy coffee. But here you can see that if you have a rapid rotating system like this, the creamer gets kind of stuck and it can't diffuse out. And this is exactly what we expect to happen inside the cores of planets too. So we use experiments like this to really try and understand what goes on inside planets. So I see a question about why are the magnetic strings concentrated at the poles when they're the same distance from the center as the equatorial region? So that is an open question. We talk about that as being a very dipolar field where you have all the field lines coming out of one end and going into the other. Just like if you have a bar magnet, you would see the same thing. And the answer is that it turns out that it seems to be the easiest type of field for a planet to create. We think that the rotation of the planet is part of that reason. And that's, so basically you'll notice that the North Pole and South Pole are where our rotation poles are as well. And so because of things like you see in this picture, because motions tend to know about the rotation axis, it turns out that creating dipolar fields with the field lines concentrated near the poles tends to be favorable. But then you have planets like Uranus and Neptune that aren't doing that. They're doing something completely different. And so that's really an active area of research. All right, so I just want to summarize quickly here. Studying planetary interiors is hard. I hope I've made that clear. But it's also fascinating. There are so many cool things we're learning about in terms of the processes that happen deep inside planets, how those affect things happening on the surface, and also what happens to materials. So with that, I'm going to stop. I'm going to say thank you, and I'm happy to take any questions.
Thank you. All right. So what I'd like to do is ask everybody to turn on your camera if it isn't turned on. And if you have a question, please use the little smiley face down at the bottom to raise your hand. and hopefully I will see you. And so Shannon's already raised her hand. But before we get to Shannon's question, there was a question in the chat that I wanted to make sure that we got to, which was, you talked about your thesis study being about planets that don't have the same kind of polarity that the Earth does. So what did you find out at the end of your study?
It's a great question. Okay, so this is actually, I tell this story a little bit in the book. So when I was doing my thesis, one thing we proposed is that the reason Uranus and Neptune's fields might be so different is because the area, the volume where the dynamo is being generated is just a very thin shell near the outside of the planet. So the length scales involved are thinner, and so you might get smaller scale fields. Now, when we did that, a big question that came out of that is like, well, why? Why would Uranus and Neptune only have this tiny dynamo region? What was going on inside of that shell? And at the time of my PhD, I had to be like, well, I don't know, but you know, these are big planets and the pressures and temperatures are really high, and we don't know what happens to materials as they get under higher pressures and temperatures. So that's the status we were in. Now, one of the most amazing experiences of my life was in, I think it was like 2008. So this was maybe 4 or 5 years after my PhD. Someone wrote a paper with an explanation for why, and it was because they had discovered this new phase of water called superionic water.
Okay.
And they discovered that it would happen in Uranus and Neptune below this thin shell that we had found. So suddenly I had a reason for why I had this explanation. And so that was incredibly satisfying. And then in very recently, I'm going to get the year wrong, but in the last few years, they've actually experimentally made superionic water in the Sandia National Labs thing.
Maybe
so
that's
like,
what we get when we go to the spa. And
yeah, exactly.
They're super ionizing the water that we get to drink. But no, not really. Yeah. So does that mean that those planets have super ionized water, or that's very speculative?
So I would say that's a theory. That seems to explain the observations we have, and there's a physical basis for it. Okay. Is it we don't fully understand the system, and we don't know. So one thing that happens when you do experiments and stuff is you just use water, for example. And then you say, well, Uranus and Neptune aren't only water. There's a little bit of gases in there, there's a little bit of carbon, a little bit of other things. So you start sprinkling the water with other things, and then you put it under really high pressure and you ask, does the same thing happen? And that's really where active research is happening right now, is what happens when you don't just have pure substances at these things.
Mm-hmm. Okay. Shannon, please unmute and ask your question.
I'm so excited. This is awesome. Thank you so much, Dr. Stanley. I have 2 unrelated questions, and hopefully you can answer them quickly. One of them is, I don't understand why the magnetic fields are stringy at all. Okay. Mm-hmm. And the second question is, can you do seismology on the big gaseous planets? Is there some?
Mm-hmm. So 2 great questions. All right, the stringiness. So magnetic fields, the way I think about it is that's just a visual presentation of what fields look like, of how to represent the fields. The magnetic field is everywhere. It's not like there's a string of magnetic field here and then nothing and then another string here. But what people try to do is they try to follow what's called a line of force. So where is something kind of connected? And that's where magnetic fields are connected on a line of force. So the magnetic field, some property of the magnetic field is constant there, but there's definitely magnetic fields everywhere. But that's really just contouring a specific feature of the magnetic field. So did that answer that? That helped? Okay, the second question. So this is a great question too. So another place you could ask the question, if you have a giant planet, something that doesn't have a surface, can you do seismology? And the answer is kind of. And we've actually done this for quite a while on the sun. So the sun is a gas ball as well. And we can actually see the surface of the sun do little vibrations. And those vibrations are really sound waves going through the sun. And they get stoked by kind of like if something kind of punches the sun, nothing punches the sun. But if some sort of motion happens inside the sun, that can cause a bunch of waves to occur, just like if you drop a rock in a pond. And we can watch those on the surface, and from that, figure out what goes on inside. People want to do this for the gas giant planets. It's harder because there isn't as much hydrogen and helium in them. They're smaller, but people are trying. No one has yet successfully done it, but there's work going out there trying to see if they can see basically what are called the vibrational modes of planets.
Thank you.
Thank you.
Okay. There's another question in the chat. Can you speak more about how you collaborate with scientists working around the world? And this connects to a question that came in before, which is what do you do with all the data coming in from the different missions to other planets? So how does that all work?
Oh, that's a great question. So when you're working on a mission like the NASA InSight mission was the first mission I've ever been involved with. Before moving to Johns Hopkins about 5 years ago, I worked in Canada, and I was much more kind of on the computer simulation side of things. But when you have a mission, it's always an international effort. So InSight is a collaboration between NASA and the European Space Agency. We are always trying to work with our partners in international locations as much as possible, right? Hundreds of scientists are working on these sorts of things. When it comes to day-to-day work, that's more, so my research group, which involves a range of graduate students, undergraduate students, postdoctoral fellows, and so they're also international. I have representation from all over the world in my research group, so that's always amazing. And so when we try to do these collaborations, it's really because you know that people can bring different things to the table, and having all that knowledge and different ways of interacting and different ways of thinking about things, it just makes things so much better. That was the first question. Was there a follow-up to that?
There's so much new information coming in. How do you sort through what is going to be useful to you, is going to completely throw out the ideas that you've already had? How do you work with just that barrage of information?
It's overwhelming. I'll be honest, it's completely overwhelming. But the way that planetary missions go is we know that every time we send a new mission somewhere, it's going to change our understanding of that place, right? Because we're going to get more data, better data. But in planetary science, we also always know we don't have the full picture. So, when we sent our first mission to Jupiter, so let's think about the Galileo mission. So that was a mission in the mid-90s that went to Jupiter. It was on a particular orbit, and that particular orbit around Jupiter allowed it to measure certain things. And from that, we've created hypotheses about what we saw. Then we sent Juno there. Juno's on a completely different orbit. It's with more advanced instruments because it's later in time. We've advanced our technology. And we can now see how we have to change some of our understandings of it. And it's not that what we had previously was wrong. It's just that we kind of have more details now, or we can kind of reduce error bars on things, or we can explain things we found that we weren't expecting to see. A lot of this, it really involves, scientists have to talk to each other a lot. That's probably why we have so many conferences and things like that where people present their work. You really have to kind of stay on top of what's the newest thing from this mission, right? And most of the missions, like NASA missions, the data becomes available like within a few months. All the data from the missions is dumped on the internet, and anyone can work with that data, right? But you really have to kind of keep up with things. It's really a matter of, staying in contact with colleagues, going to conferences, reading the papers, figuring out what everyone else is working on.
I have another question. You showed that demonstration of the creamer being poured into basically a glass of water, but because it's rotating on the record player, it doesn't disperse the way it does in your coffee. Instead, it forms a sort of amorphous column. So creamer is mostly water. It's being poured into mostly water. It's not under all that pressure and heat that you were describing in the interior of even the Earth, let alone other planets. So how do you translate, okay, this is doing something interesting because of rotation, but how do you know then whether your ideas about how it's working inside the planets are actually real? I mean,
it's a wonderful question. And it's actually, so fun story. So when students go through grad school here, they have something called a qualifying exam, where they get asked questions by their professors. And this is a question we ask them all the time, right? How do you know that your tabletop experiment is actually doing what you want it to do? And the answer is the fact that it turns out, and this is something that's very true about fluid mechanics in general, is when something happens in a fluid, let's say you get waves that form on the surface of the ocean, it's not so important what the length scale of the ocean is or what the temperature of the water is, but it's some combination of those parameters that determine the dynamics you see. So what we have to do is we have to figure out what combination of things like the fluid length scale, the velocity, the temperature, the gravity, what combination of those things is actually the important number that determines what the body's going to do. And when we find that number, we can make it on a tabletop experiment by tweaking things. So maybe we can't get the length scale of the core right, but we can make the velocities faster. And as long as that combination of parameters is the same, the dynamics is the same. And this is how so in fluid dynamics, they do things like when they train people how to kind of steer tugboats to bring in big ships, they do it in these little ponds because they've found a way to make those numbers the same. And so it's how we do experiments at small scale.
Yeah, well, I could keep asking you questions for hours, but we are running up against the end of our time. I want to thank you so much for you coming and telling us about your work. It's fascinating. We can't wait to read more about what you and your team find out. And for everybody who's here from SAQA, I hope that you leave feeling really inspired and excited, and that you will check out the call for entry for Fierce Planets, which will open next July. So you have a lot of time to really experiment, to explore, and to create wonderful art for a traveling exhibition that will be connected with Dr. Stanley's book. Before we leave, I wanted to ask you, I know you and the editor, Anna Burgard, came up with the title of Fierce Planets. Can you tell me a little bit about why you wanted it to be called Fierce?
Oh, that's a great question. I think it's ultimately because when you think about planets and you think about what happens inside planets, there's like no holds barred, right? It's like they do things that we never thought would be possible. And so that just translated ultimately into Fierce. I think Anna was actually the one that came up with the phrase.
Yeah, I'll just chip in here a little bit. And just one of the things I love about the subject is how serene planets look, but inside there is this volatility and all of this, interest and motion that kind of belies the surface, what's on the surface. And so, I mean, that's one of the things. And it's, we spend so much time thinking about the surface and much less thinking about the interior and how that interior impacts our surface, other than knowing if there's an earthquake, a tsunami might result, and things like that. But there's so much more. Like the magnetic fields and the northern lights and all of this, so much that we're going to learn from this book. So, and I just kind of like the quote unquote street use of the word fierce, just like that it's cool, right? So,
well, that's great. Thank you both so very much. This has been an incredible treat, and I can't wait to see what art results from this presentation.
Yeah. Thanks, Martha.
Thank you so much. Thanks everyone for listening.
Thanks, Nina.
Thank you.